So now we're going to talk about how to represent friction. And friction, as we mentioned last time, comes in three flavors. At the surface, which is the one that drives the motion, and the friction at the bottom, which retards the motion, and friction in the water column between the surface and the bottom. And that also tends to retard the bottom. But which one retards the bottom? Retards the flow. Which one retards the flow more? The bottom friction or the internal friction? Which is greater? Greater. Bottom friction or internal friction?
Bottom?
The bottom friction. Silly question, but just wanted to make sure. So in general, again, there's a way to derive all these terms, but in general, the frictional terms may be represented by those three contributions. This would be the horizontal component in the x direction, the horizontal component in the north direction, and the vertical component. So if you look at these three terms, they represent a stress divergence, the divergence of the stress. And that's what friction is. How much does a stress applied on the flow changes with space. So it's a stress divergence. You will hear this term, some people refer to this term as a stress divergence term. Some people call it friction, some people call it mixing. Any other ways in which you've seen this term referred to? No? So at the surface, how can we parameterize? It's very hard to measure this term, so we use parameterization. This is the crux, a very basic and very important problem in fluid mechanics in general. And in coastal oceanography and coastal engineering and physical oceanography, how to determine this term is a very big question. And up to now, we've been using parameterizations on how to represent this term. So the technology is now allowing us to start measuring this term, as we will discuss throughout this class. That this is one of the big open questions still in our field, how to measure or represent this term. So up to now, we use parameterizations. How do we parameterize these terms? At the surface, friction at the surface. What happens at the surface? We have the wind blowing, for example, and that causes a stress. Right? So at the surface, we parameterize the wind. This term on the right-hand side here, this stress. So the term in the brackets is a stress. So the stress is parameterized as a tau over rho. Rho is density. Tau is given by this expression, which is density of the air, a drag coefficient that represents drag between air and water. How much is that? What's the value of that drag coefficient typically? There's a canonical value. Well, not a canonical value. There are parameterizations for that drag coefficient. Does anybody know at least the order of magnitude of that drag coefficient?
10 to the minus 3.
10 to the minus 3, right. It's around 1.14 times 10 to the minus 3, but that should increase with the wind speed. So it's a function of the wind speed, that drag coefficient. What are the units of that drag coefficient? Of this drag coefficient? What are the units? Let me go to the term on the left, the density of the air. What's the value of the density of the air? And its unit? How much does a cubic meter of air weigh? Do you feel it? We carry it all. Well, it's not all of it on us, but how much does a cubic meter of air weigh?
1 kilogram.
1 kilogram approximately. It's a little more than 1 kilogram. Depends on temperature and humidity, but it's approximately just a little more, like 1.2 kilograms per cubic meter. Right, so it has units of kilograms per cubic meter. Let's go to the other two terms here. This is the x component of the wind velocity. So that has units of what? Meters per second. And this is the speed of the wind. which also has units of meters per second. So you have kilograms per cubic meter, you have meters squared per second squared here, and you have this density, so this density goes with that density. And what units should we have here? Remember, we talked about this term having units of what? Meters squared per second. And here we have 1/2. So the units of this should be what? Meters squared per second squared, right? This term on the left-hand side, this term should have units of meters squared per second squared. So right here, the units of this density go with the units of this density, so we have meters per second times meters per second. So the units of the drag coefficient, no units, right? It represents an interaction with the air and the water, but it has no units. It's a dimension of one. Okay, so that's at the surface, and this type of parametrization has been used extensively, I would say, for the last 60 years or so. So analogously, at the bottom, what would you say? How would we parameterize that same term, the A sub z du dz? We also use a bottom stress. Notice that I've sort of tried to differentiate the surface stress as tau sub s from the bottom stress, which is tau sub b. Now we have tau sub b is approximated by density of the water now, not density of the air. What's the density of the water, we said? Fresh water, what's 1,000 what? Kilograms per cubic meter, right? You know, it really, literally weighs a ton, right? A cubic meter of water weighs a ton. So, among all of us, we might be able to lift 1 cubic meter of water. That's 1,000 divided by 10. What's that, 100 kilos each? Not even all of us would be able to. So imagine that. Okay, so that the density of water is order 1,000 kilograms per cubic meter. We have density in the denominator too, so it goes away. So U is the component, the east component of the flow, and this is the speed of the current near the bottom. So this is also a what? A drag coefficient. That's a drag coefficient with dimensions of no dimensions. What are the units? What's the value of this? For this, there is a less variation from a canonical value that people tend to use. Same order of magnitude as this one in the air. Same order of magnitude, but should it be larger or should it be smaller? Which is easier, to move water from the air or to move the bottom, for the water to move the bottom? For the wind to move the water or for the current to move the bottom? Which is easier? For the wind to move the water, so the drag coefficient should be less for the air-water interface, right? But for the water-sediment interface or water-bottom interface, how much larger approximately?
2.5.
2.5. 2.5 times 10 to the minus 3 is the drag coefficient. So notice that drag coefficient, or this bottom stress parameterization rather, can be also linearized. It is non-linear because it requires a product of two velocities. But it can be linearized by this expression, R times U, where R is a linearized bottom drag coefficient, and that bottom drag coefficient is approximately equal to the bottom drag non-dimensional times the speed of the current. So the units of that that linearized bottom stress coefficient are what? What are the units of that R? You can see it from here. Meters per second. So you have to be aware of these distinctions on how to parameterize the bottom stress. If it's a linear parameterization, it requires a coefficient that has units. If it's a nonlinear parameterization, it requires a coefficient that is non-dimensional. You know that, right? Now, what do we do at the interior? This is the crucial part in fluid mechanics. How to parameterize these A's sub z du dz. How can we parameterize these A's sub C du dz in the interior of the water column. Have you heard of any ways of doing it? For those of you who use models, you should know. Or you use a turbulence closure, because ultimately, what this stress in the middle of the water column, what it parameterizes, it tries to parameterize the exchange of momentum, the vertical exchange of horizontal momentum. How much momentum goes in the vertical direction as related to the horizontal flow. That's what happens at the air-water interface from the wind, and at the bottom from the current interacting with the bottom. In the interior of the water column, it's just different layers of water interacting among each other. And that's a more difficult problem to address, and we don't have a good parameterization yet of that. So that's a fundamental question that needs to be resolved. So if you come up with a parameterization that can be applied universally, then you become very famous. So we tend to use parameterizations that are a function of the Richardson number, where the Richardson number is a ratio of the energy of the water column that tends to stratify it. That is here the stability of the water column in the numerator. So it's the energy that is applied to the water column to increase its potential energy. So it's the stability of the water column divided by the energy that's applied to the water column to try to de-stratify it, which comes from the vertical shears. So the Richardson number looks at the competition between the stratifying tendencies and then de-stratifying tendencies, right? So we tend to parameterize these, in particular the eddy viscosity, the A sub z. We tend to parameterize it as a function of the Richardson number. So if you use a numerical model, you have to get a solution for those terms. So, and you have to parameterize those terms in some way. Even if you don't use a numerical model, if you just try to solve the dynamics analytically, you need to parameterize those terms. And this is where the difficult part comes. Again, we will, later on in the course, we will dedicate more time to that part. So we've seen how to represent the pressure gradient and how to represent friction. Tides, we said that it's a boundary condition. It's just a sinusoid that we prescribe to our problem. And then gravity and Coriolis. How do we represent gravity? Gravity only acts in the vertical. So what is the gravity vector acting in the water, in the ocean? Again, so how would you represent the three-dimensional force? Maybe like that. Right? 0 in this direction, 0 in the north direction, and in the vertical direction you have the acceleration due to gravity, which is 9.8. Doesn't change that much throughout the planet. The Earth changes just a little bit, maybe less than 1% from pole to the equator. But what are the units of this? 9.81.
2 seconds squared.
Very good. And then, if you represent gravity like that, how would you represent Coriolis? About something like that. What does that mean? Does that look familiar to anybody? Maybe not to everybody, but to anybody. So in the horizontal, in the east direction, we have the V component of the flow acting. Why is that? Why is the V appearing on the X component of the motion? Because Coriolis tends to deflect motion in a normal direction, right? To the right in the northern hemisphere, to the left in the southern hemisphere. So a U motion, a motion in the X direction, a U motion, tends to be, or the Coriolis acceleration tends to produce a V motion. And we have the negative sign for the U component, no negative, positive sign for the east component, for the north component. And that F, what does that F represent? Coriolis what? What do we call it? Coriolis parameter. That F equals, yeah, I know that Amy's stressing to answer all these questions. She's seen these many times. So the Coriolis parameter is twice omega. What does omega represent here?
Rotation of the Earth.
The rate of rotation of the Earth. So it's right there. 1 revolution in 24 hours. And this lambda is what? The latitude. So the Coriolis parameter is greater at the equator or at the poles? At the poles, because lambda acquires, the sign of lambda is maximum at the pole, and is 0 at the equator. So the Coriolis, the effects of rotation of the Earth are greatest at the poles and are negligible at the equator. So that's just a reminder. And so all comes again from the mother of all laws, the Newton's second law, that when we expand that into all the equations that we have collected, we get this framework. So when you try to address any problem in fluid mechanics, and in particular in the ocean and in estuaries, then you have to solve this set of equations. And notice that the equation of state that I put there is a simplified version. We need 2 more slides just to represent the equation of state of seawater. So we have the 3 momentum equations. Notice that in the vertical, we can approximate the vertical momentum equation to this expression, which is what? We call it the hydrostatic approximation. So strictly, in the vertical direction, you would have an analogous representation as this one and that one. But the other terms that are different from these two are many orders of magnitude, like 9 orders of magnitude smaller. However, there are places in the ocean and in estuaries where you have large vertical flows, where this hydrostatic approximation is not valid anymore. And people are starting to develop, or have been developing in the last decade or so, non-hydrostatic models, where they represent the vertical component of the flow in its true fashion. So can you imagine when one of those terms, one of these acceleration terms, or these frictional terms, can be larger than gravity? That is a non-hydrostatic approximation. Is it possible? No? How about in a waterfall? What's the dw dt term? Or w, the vertical velocity, how large is that? So you can start imagining that in those circumstances, the hydrostatic approximation will not apply. So then we have then this equation that we call what? Conservation of mass or continuity. Then we have conservation of salt, conservation of heat, and the equation of state. So every time we attack a problem quantitatively, this is what we have to start. This is where we start. If we want to simplify the problem, then we can say, okay, some of these terms are not relevant, but we have to show why they're not relevant. And then we might be able to solve the problem exactly, that is analytically. Otherwise, we'll have to go to a numerical solution and put this in a numerical model, like some of you have done. All right, any questions up to here? All right, so